Section 7.4, Integration of Rational Functions by Partial Fractions. In this section, we will learn a process to break down a fraction so that it may be easier to integrate. Consider the fraction below. We see that when we subtract and collect like terms, we get a different form of the fraction. So we're comparing these two forms of our fraction. Which one would you think is easier to integrate? Of course, this one, right? It might seem impossible to integrate our result, but it would be possible to integrate the two fractions we started off with. This is the goal of the section, breaking down rational equations. We will now go over 4 different, kind of feels like 5, methods that we may approach integrating rational equations using decomposition of fractions or partial fractions. Whenever possible, try to perform long division. And we do this whenever our numerator is larger than our denominator. If we're starting off and we're analyzing our problem and we see that we can't do any type of integration we learned so far, so it's something from the past, doesn't fit any of our new integrating identities, and we can't use substitution, try to divide. All right, let's perform long division. Now, because this one, you're dividing by a linear factor, if you wanted to, you can proceed using synthetic division, which is something you should have seen back in college algebra and also again in pre-calculus. But let's do long division. All right, so our divisor is x minus 1 and our dividend is x cubed. We don't have an x squared, so write 0x squared plus x plus 0. Okay, so you begin by dividing your first initial numbers, our x and our x cubed. I always like to show my thought process on the side. X cubed divided by x gives us x squared. So we have x squared. Then you multiply to your outside so that we have x squared times x is x cubed. X squared times negative 1 is negative x squared. From here, we change our signs. Okay, x cubed minus x cubed is 0, which is always a good step, or a good way to show you're on the right track. 0x squared plus 1x squared gives us 1x squared. And then you can bring down all your remaining terms from there. Let's divide again. All right, so now we're dividing x squared by x. So we just get x, positive x. We're going to multiply two numbers on the outside. And we have x times x gives us x squared. X times negative 1 is negative 1x. We change the signs. And we get 2x. Let's divide again. We get 2x divided by x, we get 2. And we're left with 2x minus 2. We change the signs, and we're left with a 2. So after dividing, we're left with x squared plus x plus 2 plus our remainder divided by our divisor, x minus 1 dx. And we see this is much easier to integrate. Remember, you integrate by terms. So we have x squared dx plus x dx plus integration of 2 dx plus integration of 2 over x minus 1 dx. So we see for the first set of terms, we just use our basic integration techniques. So we have x cubed over 3, x squared over 2, 2x. And for that last one, we factor out a 2, and we're left with just ln of x minus 1. Don't forget your constant. Now, for some of these future problems, we're going to start off by using long division and then perform our partial fractions. All right, I have some helpful hints as we prepare to work with partial fractions. Our first technique is long division is always helpful when the numerator is larger than the degree of the denominator. So whenever your numerator is a higher exponent than your denominator, then that means start off by long division. When setting up partial fractions, linear factors always have a numerator that's a constant, and we'll see these in very future examples. 3, every degree of a factor must be represented. So we have something like x plus 2 quantity squared. We need to have an x plus 2 and then an x plus 2 squared. And we'll see this again with these examples we're going to be doing. Last rule is if the denominator is not linear, so something that has like an x squared or an x cubed or something along those lines, then the numerator will have an x, such as ax plus b. The following cases will show all the possibilities, but the general rules above are a good guide. All right, case 1. The denominator q of x is a product of distinct linear factors. Distinct just means different. All right, let's take a look at this example. To begin, we see, well, you have to analyze each problem first, right? So we see u substitution wouldn't be ideal because we have all these different copies of x. Usually we have a u and its derivative, so this wouldn't work. This doesn't fit any of our integration identities that we've learned in the past couple of sections. So partial fractions seems to be our ideal method. Now, how do we do this? Well, we first have to simplify by factoring our denominator as much as possible. So after we factor our denominator, I'm taking a look at only the denominator. This factors to be, you can factor an x, and then the quadratic factors to be 2x minus 1 and x plus 2. All right, now let's set up our partial fractions. Now we see each one of these factors is linear, meaning my degree of my x is 1. We don't have an x squared or an x cubed. So because of that, I'm going to write a numerator for each one of those as a number, a constant. All right, as we set up our partial fractions, we have to write our initial problem. So we have x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x is equal to, first we have the x plus, then we have the 2x minus 1, and then we have the x plus 2. Now each numerator is what we're going to find. So our hope is that we're going to have to integrate only this, which is something we can do. We need to find the numerator that goes along with it. So we're going to write a, b, and c. And we know we only need a, b, and c because, again, each one of these factors is a linear factor. Okay, from here, let's go ahead and simplify this equation. We have an equation we created. All right, so we're going to simplify by using some algebra. So let's multiply both sides of our equation by our greatest common factor, or in this case, our greatest common denominator. Greatest common denominator. In this case, it's going to be an x, 2x minus 1, and x plus 2. Let's multiply that to both sides. That's going to make this denominator cancel, so that we're left with and x squared plus 2x minus 1. With our a, the x is left canceling, so we're left with a times 2x minus 1 and x plus 2. For our b, our 2x minus 1 canceled, so we're left to multiply that by x and by x plus 2. For our c, our x plus 2 canceled out, and we're left to multiply that by x and 2x minus 1. All right, from here, let's go ahead and multiply. Let's expand our right-hand side. So we're going to have to go ahead and FOIL. So you can go ahead and FOIL these two. So we're left with 2x squared plus 4x negative x negative 2. We have 2x squared plus 3x minus 2. Multiply the a, and we're left with a 2x squared plus a 3x minus 2a. Let's multiply the b's. We can multiply the bx times each one of those, and we're left with bx squared plus 2bx. We can take the cx and multiply it by the 2x, and we're left with 2cx squared minus cx. And what is that equal to? 2x squared plus 2x minus 1. Okay, from here we want to group all of our, okay, so let me tell you, our hopes is to set up our constants with our variables. So what we're going to do is we're going to group all of our x squares, then we're going to group all of our x's, and then we're going to group all of our constants, so the ones that don't have x's. So we see that we have ax squared, so we have, I'm sorry, a2, so we're going to write 2a for a2. We also have a bx, so we're going to write a b plus b. And we also have a c, a positive 2c, so plus 2c. Let's take a look at our x's. We have 3a, a positive 3a. We have a 2b, a positive 2b, and a minus c. And our constants, all that we have left is just that negative 2a. And we have that set up with 1 x squared plus 2x minus 1. So what we're going to do next is we're going to group them in such an interesting way. So they're equal to each other. So we're going to group that 1 with that 2a plus b plus 2c. That 2, since it's paired up with the x, we're going to pair the other one that has the x. And lastly, the negative 1 with the constant. Let's set those equal to each other so that we have three linear equations. For our x squareds, we have 2a plus b plus 2c, which is what we have here. We're going to set it equal to 1. And we're going to do that to all of our constants. Next, we have 3a plus 2b minus c is equal to 2. And negative 2a is equal to 1. Okay, luckily we get one straight off the bat. We get a is equal to negative 1/2. Let's find another variable. When I'm working with linear systems or linear equations, I always like to number them to keep from making a silly mistake and to keep track of my work. All right, so we have an A. How about we work with two equations to cancel a variable? Let's cancel C. So let's take equations 1 and equations 2 to cancel the C, since we see that's an easy one to cancel. We take our equation 1, so we have 2A plus B plus 2C equals 1. And let's take equation 2 and multiply it by a 2, so that my C's can cancel. And now with that change, we're left with 6A plus 4B minus 2C equals 4. Let's go ahead and add them. We have 8A plus 5B, those cancel, is equal to 5. Now we know one of them. We know A is negative 1/2. We can plug that in for A, and that'll give us B. Okay, so to find B, we have 8. My A is negative 1/2, plus 5 times B, which we don't know what that is 5. We're left with negative 4 plus 5B equals 5. We add 4 to both sides. I have on my notes that B is equal to positive 1/5. But working this out here, I see that we're getting 9/5. So as you're working this problem out, keep an eye out for a slight algebra mistake, since I think there's a possibility of one. All right, so B is supposed to be 1/5. We know A is negative 1/2. You plugging those back into our first equation, we have 2A plus B plus 2C equals 1. We said that A is negative 1/2. B is 1/5. So C, once we plug those in, C is left to be negative 1/10. So with that said, we have now found this A, this B, the C are the constants that we have in our equation. So we have now managed to break down this initial fraction to something that's a bit more easier to integrate. All right, let's rewrite what we have so far. So with those coefficients, we have the integration of 1/2 times 1x plus 1/5 times 1 over 2x minus 1 minus 1 over 10 times 1 over x plus 2. Again, we just found the coefficients, the numerators that go on top of each one of our breakdowns. All right, we can go ahead and integrate each one of these separately. And now we can just use our integration for a fraction of 1 over x, which will result in ln. So for the first one, we have 1/2 ln of x, 1 over x, plus 1/10 ln of 2x minus 1. And we have that 10 because we take the denominator of our 2x, minus 1/10 times ln of 1 over x plus 2, plus c. That's really cool. Now again, let me just go over this problem again. So we were given a problem that we cannot integrate. Well, we can use partial fractions. We can go ahead and factor our denominator, such as we did here. We can factor our denominator, and that would put us to partial fractions. Now, because each one of our factors is linear, we're going to write a numerator of only a constant, a, b, and c. Our goal from here on out is to find those constants. So we solve the equation by multiplying both sides by our greatest common denominator with the hopes of canceling out the denominator. That should cancel out your denominator. All right, so we're now here. Now from there, we want to multiply fully, and from there we want to group our terms that have the same variable. In this case, it was the x squares, the x's, and the constants. We do this so we can perform or create a system of linear equations using only the coefficients and setting them equal to each other. So as we see, 1 is equal to the 2a plus b plus 2c. The 2 will be equal to the 3a plus 2b minus c, and the minus 1 will be equal to the negative 2a. We solve the system to find those coefficients, and then we can go ahead and from there hopefully integrate. Now with each one, we mainly have to see different examples using different denominators. Let's take another case. So let's say we factor, we have different factors of the same denominator, or different powers of the same denominator. So as we see here, we have x squared and x minus 1 cubed. Because we have the x squared, I have to write an x and then an x squared. Because we have x minus 1 cubed, I first have to write x minus 1, x minus 1 squared, and x minus 1 cubed. So I have to have a copy of each factor until I reach its highest degree. And that's if we have a factor that has, for example, like a multiplicity in a sense. All right, let's take a look at this next example. We can go ahead and factor the denominator by grouping. If we factor, it factors to be x squared minus 1 and x minus 1. So if we group the first two and the last two in factor, we see that we can factor again. Right here we have differences of squares. That factors to be x minus 1, x plus 1. So now we have two copies of x minus 1. So we have x minus 1 squared and x plus 1. So to set up our partial fractions, we have to have it set up this way. We have to have a setup such that we have x minus 1, x minus 1 squared, so we have it squared, and then I can write that x plus 1. All right, so that's what we're going to see for this partial fraction. Let's analyze this problem a bit first. So we see here, looking at the degrees of our polynomials, our numerator is larger than our denominator. So our first step would be long division. All right, after long division, we're left with the integration of x plus 1 plus 4x divided by x cubed minus x squared minus x plus 1. Now we see here that partial fractions is still going to have to be used with our remainder, but we know what our setup should be. Okay, we're going to only focus on this one portion where we have to work with our partial fractions. Let's go ahead and break that rational polynomial up. All right, so we have all right, so we have 4x over x cubed minus x squared minus x plus 1. Now we see that each one of our factors is linear. So we see here we have a linear factor. Even though it's squared, the factor itself is linear, and so is so as well there. So each one will just have a single variable. So we're going to have a over x minus 1 plus b over x minus 1 squared plus x plus 1 c over x plus 1. All right, let's repeat the same process that we did for the first problem. So let's go ahead and multiply both sides by our greatest common denominator. That should make this cancel here. And we're left with 4 is equal to a. That's going to make one of the x minus 1's cancel. So we're left with x minus 1 times x plus 1 plus b times the x squared is going to cancel. We're just left with x plus 1 plus c. The x plus 1 cancels, and we're just left with x minus 1 squared. Let's go ahead and expand. Let's multiply it out. All right, we see that these are differences of squares. So it's going to be x squared minus 1. So we have a x squared minus a. You just multiply the b out, so we have bx plus b. We know that's squared, so it's going to be x squared minus 2x plus 1. Let's multiply in the c. We have cx squared minus 2cx plus c. All right, that's equal to 4. So let's go ahead and group our x squareds. So we have a plus c x squared plus b minus 2c. Those are the ones with a variable of x, plus negative a plus b plus c are our constants. Let's group them. Now here notice we don't have an x squared. We don't have an x. We just have that constant of 4. So we're going to let our x squares equal to 0. So we have a plus c equals 0. We don't have an x, so we have to set that equal to 0. We have b minus 2c equals 0. But we do have a constant, so we have negative a plus b plus c equals 0. All right, let's go ahead and solve this system of linear equations. Again, I like to number them for the sake of referring back to them. So 1, 2, and 3. So as I'm looking at these, I see that if we go ahead and cancel a using equations 1 and 2, we can work with b and c only. So let's go ahead and do that. Let's take equation 1 and equation 3 to cancel a. So equation 1, and we chose that because our a's easily add up to 0. So we have a plus no b plus c equals 0 for equation 1. Equation 3 gives us negative a plus b plus c equals 0. Those cancel. We're left with b plus 2c equals 0. And now we can take equation 2 and our new equation. That's our new equation. We can add those two or work with those two to work with B and C only. We see that our C's add up to be 0. Equation 2 is B minus 2C equals 0. Our new equation is B plus 2C equals 0. And we're left with, I didn't set that constant equal to 4. So I made a mistake right here. I'll just write over it. This was supposed to be 4. So our equation 4x. That should have been x, so this one should have been 4. And that last one was 0. That was correct. So I only have a mistake right here besides that initial one. Where I wrote equation 2, that should be equal to 4. Okay, let's continue. So many room for mistakes. So that we have 2b, my c's cancel, equal 4. We're left with b equals 2. All right, I can go ahead and work backwards now. We can plug it into our new equation or to equation 2, whichever one you want since you have options. So we plug it into equation 2. We have b minus 2c equals 4, and we now know that b is equal to 2. So left with 2 minus 2c equals 4. C is equal to negative 1. We can go ahead and take equation 3. Negative a plus b plus c equals 0, since we now know that b is equal to 2 and c is equal to negative 1. And so we're left with c or b, a is equal to 1. Okay, let's go ahead and rewrite our integration problem. So we are integrating, what do we have? We have x plus 1 and then our new equation. X plus 1. We're going to have this equation here. We said that a is going to be 1, b is going to be 2, and c is negative 1. So we have that new replacement for this circled problematic term. Let's write that down. So plus 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1. And we can go ahead and integrate pretty easily. For that third term, that fourth term, you might want to use substitution to keep track of your answer, so that we have x squared over 2 plus x plus ln of x minus 1 minus 2 over x minus 1 minus ln of x plus 1. Now, just to take a look here, we see that we can use our laws of logs. We can use that difference one that says that ln of a minus ln of b is the same thing as ln of a over b. So you can write that as a final answer of x squared over 2 plus x minus 2 over x minus 1 plus ln of x minus 1 over x plus 1. And this actually gives us an identity, which we'll see in the future, very near future in this section. All right, let's continue. A helpful integral that we will see in this next problem is the integral of 1 over x squared plus a squared. It's the same as 1 over a tangent inverse of x over a plus c. So this is when one of the factors of our denominator is not linear. All right, so we have, for example, just to see the setup, say we have x minus 2, which is linear, so that's going to have a constant, a one variable, x squared plus 1, that's non-linear. It's actually a quadratic, right? So as our numerator, we're not going to write b, rather we're going to write bx plus c. And our next one, we see it's also nonlinear, so we're going to write an x plus a constant, but using the next letters of our alphabet. So dx plus e is a good option. Let's take a look at our next example. So for our next example, we see that once we factor, our denominator will be x times x squared plus 4. We notice that we have one linear factor and one nonlinear. So the linear one's going to have a numerator of a, the nonlinear is going to have a bx plus c. Okay, let's go ahead and set up our partial fractions. Now here in this problem, we didn't have to worry about first applying long division since my numerator is not larger than my denominator in the sense of the degree. All right, let's go ahead and write our setup. So we have 2x squared minus x plus 4 divided by x cubed plus 4x is equal to, we're going to have that x plus that x squared plus 4. Now what's new about this case is that non-linear case. So we have a for the linear and bx plus c for the nonlinear. Now if we were to have more copies of it, we just keep following that list of letters in our alphabet. Okay, let's do the usual. Let's go ahead and multiply both sides by our greatest common denominator. In this case, it's going to be an x and an x squared plus 4. Let's multiply that to both sides. That's going to make the denominator cancel. And we're left with 2x squared minus x plus 4 is equal to a. My x canceled out, and we're left with x squared plus 4 plus bx plus c, and that's going to multiply with an x. All right, let's go ahead and multiply fully. And we're left with 2x squared minus x plus 4 is equal to ax squared plus 4a plus bx squared plus cx. Let's group our x squareds. Those that have an x squared, those that don't have an x to the first degree, and those that don't have an x. So that we have an a plus b. For x's, we just have that c. And for our constants, we have that 4a. All right, let's set it equal to our numerators. Our coefficients. So we have a 2 for our a plus b. A plus b equals 2. For our x, we have a -1. So c equals -1. And then 4a is equal to 4. This was not so bad to solve. So we're left with a is equal to 1. C is equal to -1, and if we plug it into that first one, we get that B is equal to 1. All right, let's go ahead and rewrite our integration problem. So we started off with 2x squared minus x plus 4 over x cubed plus 4x, which was not something we can integrate. We use partial fractions or fraction decomposition to get 1 over x plus x minus 1 over x squared plus 4 dx. And we can go ahead and integrate each one of those terms separately. Now in the beginning, I gave you an identity for integration, and it works with that second term. So let's go back. That says we have something squared plus something squared. That can be 1 over tangent inverse of x over a plus c. All right, before we get there, let's go ahead and split this fraction. Now, I'm not talking about partial fraction decomposition, but we see that this x squared plus 4 applies to the x, and it also applies to the 1. So that can be written as the integral of x over x squared plus 4. Let's factor out the minus for that second term, minus 1 over x squared plus 4. Let's bring down that initial one. I'm forgetting my dx's. Okay, we can go ahead and integrate. Now for that first one, it's not so bad. We just have ln of x. For that second one, you can go ahead and we have that x, so we need to use u sub. You can let x equal x squared plus 4. And so this factors, that simplifies to be 1 over 2 ln of x squared plus 4 minus that second one, we use the identity we just saw. So that's 1/2 tangent inverse of x over 2 plus c. Okay, the fourth case contains a repeated irreducible quadratic factor. So we see this, for example, when our denominator looks something like this. So we have linear, linear, nonlinear, and several copies of the nonlinear. So of course our linear has that. For the x, we have an a over x. For the x minus 1, we have a b over x minus 1. For the x squared plus x plus 1, we have c x plus c. But then we have this cubed, so we need 3 copies of that. And because it's nonlinear, each one's going to have a nonlinear numerator. So for the first one, we have ex plus f. For the second one, gx plus h. And for the third one, ix plus j. And if there were more, we just follow along the alphabet. All right, let's go ahead and do a problem. So we have to evaluate or integrate the integral of 1 minus x plus 2x squared minus x cubed over x times x squared plus 1. All right, our setup for our partial fractions. It's already factored for our denominator. So we're going to have, for this linear one, we're going to have a over x plus, now this one's nonlinear. We need to have that first copy. So we have x squared plus 1, bx plus c. And now we need another copy since it's squared. We have x squared plus 1 squared. And since it's nonlinear, we need a nonlinear numerator. So we have dx plus b. All right, let's go ahead and set up our partial fractions. So that we have 1 minus, or let me write it in standard form, negative x cubed plus 2x squared minus x plus 1 equals, well, all over x times x squared plus 1 squared, a over x plus bx plus c over x squared plus 1 plus dx plus e over x squared plus 1 squared. All right, let's do the same process. Let's multiply both sides by our greatest common denominator. That will make this denominator cancel. So we're left with negative x cubed plus 2x squared minus x plus 1. We'll have a times x squared plus 1 squared plus b bx plus c times, we need to multiply that by an x and one copy of the x squared plus 1. And then lastly, we have dx plus e. That's a quantity squared, so it just needs to multiply by the x. All right, let's go ahead and expand. If we expand, we're left with ax to the fourth plus 2x squared a plus a plus bx to the fourth plus bx squared plus cx squared plus cx plus dx squared plus ex. Let's group our x's, our coefficients, so that we have a plus b x to the fourth plus c x cubed plus 2a plus b plus d x squared plus c plus e times x plus a. And all of that is equal to negative x cubed plus 2x squared minus x plus 1. All right, let's set up a system of linear equations so that we have, in this case, a plus b equals 0. Since we don't have an x to the fourth, c equals negative 1, 2a plus b plus d equals 2, c plus e equals negative 1, and a equals 1. This was not so tough to figure out. We're left with a is equal to 1, b is equal to negative 1, c is equal to negative 1, d is equal to 1, e is equal to 0. All right, let's go ahead and plug them back into our numerators. Now, we found each one kind of separately. So we know A, we know A, we know B, we know C, we know D, and E. Once we plug them back in, we have our integral will be 1 over x minus x plus 1 over x squared plus 1 plus x over x squared plus 1 squared. All right, we can go ahead and take each term separately. For that second term, we see that x squared plus 1 applies to the x. We can split it so it applies to the 1 separately. And distribute that negative so that they each have their own negative. All right, let's go ahead and integrate. So here we see again that tangent inverse integration identity. And here you can just go ahead and use U substitution to finish the problem. All right, our answer will be ln of x minus 1/2 ln of x squared plus 1 minus tangent inverse of x minus 1 over 2 x squared plus 1 plus c. Okay, that's all the cases for partial fractions. Now let's go over that list I made in the beginning for you guys. Hopefully now that we've done partial fractions, it makes a bit more sense. All right, so going over it again, always perform log division when the numerator is larger than the degree of the denominator. And again, that's after you analyzed your integration problem and you saw that you couldn't continue using any other integration techniques. 2, when setting up partial fractions, if we have a linear factor in your denominator, set your denominator as a constant, like a, b, and so on. 3, every degree of the denominator must be represented. So we have something like an x squared plus 2. We need to have that factor the first degree up until you reach your number and your exponent. 4, if the denominator is not a linear factor, then the numerator must have an x, such as ax plus b or cx plus d. You can continue along the alphabet depending what variables or letters you've used already. And that takes care of all of your cases. You need to think about it as case by case, whether you do not need to analyze if you have case 1, case 2, case 3, or case 4. Take each one separately and just use these helpful hints. Before we finish, let's go over how we can use substitution when integrating, a different type of substitution. Rationalizing substitutions. Some non-rational functions can be changed into rational functions by means of appropriate substitutions. In particular, when an integral contains an expression of the form the nth root of g of x, then the substitution u equals the nth root of g of x may be effective, rather than what's inside of the radical like we usually do for u substitution. All right, so here we have an example. Let's let u equal the square root of x plus 4. That's your first step. Step 2 is to solve for x. So let's go ahead and square both sides. So we have u squared equals x plus 4. Let's subtract that 4. U squared minus 4 equals x. That's our third step. Our second step. Our third step is integrate for your x. So we have dx is equal to 2u, so just this derivative. Since the partial derivative, we need to write that du. Okay, let's replace each piece. So we have u will take place of that square root of x plus 4. X will be that u minus 4. And lastly, dx will be 2u du. So let's go ahead and make that change. So we said the square root of x plus 4, that's equal to u. x, what is x equal? X equal to u squared minus 4. And lastly, dx is 2u du. And there we have it. Let's go ahead and multiply. So our integration problem is 2u squared minus 4 du. All right, here we have an integration problem that we can work with. We can start off by dividing. I'll let you work your long division on your own. After long division, you'll have, well, you can in fact move that 2 forward. So that you have 1 plus 4 over u squared minus 4 du. And for this one, I'm going to use this integration technique. When you have something squared minus something squared, we can use this integration technique. So this ends up being 2, 1 du plus 4, 1 over u squared minus 4 du, so that we get 2u plus 8 because we multiply that 2. I should have written 2 times 2. So we have plus 8 times 1 over 2 times 2, ln of u minus 2, u plus 2, plus c. So our final answer is, we have to replace those u's. We have 2 square root of x plus 4 ln of the square root of x plus 4 minus 2 over square root of x plus 4 plus 2 plus c. And again, what we did here was we used this integration identity right here. So 2 times your a, that's where we have that 2 times 2. 2 times our a is 2. All right, this was 7.4, integration of rational functions by partial fractions. Your homework is 21 through 37, every other odd. Thanks.